Once the images have been registered, we're able to combine the different sequences. We've seen how we can apply this technique to a single slice of the brain. The same idea can be extended without further complexity to all slices. Now there is one volume with multiple channels that has the combined information of many different sequences. Now that we've seen how we can represent MRI data, let's turn to the task of brain tumor segmentation. Segmentation is the process of defining the boundaries of various tissues. In this case, we're trying to define the boundaries of tumors. We can also think of segmentation as the task of determining the class of every point in the 3D volume. These points in 2D space are called pixels, and in 3D space are called voxels. Let's discuss two approaches to segmentation with MRI data. The first is a 2D approach, and the second is a 3D approach. In the 2D approach, we break up the 3D MRI volume we've built into many 2D slices. Each one of these slices is passed into a segmentation model which outputs the segmentation for that slice. One by one, each slice is passed through the segmentation model in this manner to generate a segmentation for every slice. The 2D slices can then be combined once again to form the 3D output volume of the segmentation. The drawback with this 2D approach is that we might lose important 3D context when using this approach. For instance, if there is a tumor in one slice, there is likely to be a tumor in the slices right adjacent to it. Since we're passing in slices one at a time into the network is not able to learn this useful context. Let's see how we can tackle this with a 3D approach. In the 3D approach, ideally we'd want to pass in the whole MRI volume into the segmentation model and get out a 3D segmentation map for the whole MRI. However, the size of the MRI volume makes it impossible to pass it in all at once into the model. It would simply take too much memory and computation. So what can we do instead to still have the model be able to get this context information in the depth dimension? In the 3D approach, we break up the 3D MRI volume into many 3D subvolumes. Each of these subvolumes has some width, height, and depth context. So like in the 2D approach, we can feed in these subvolumes now one at a time into the model and then aggregate them at the end to form a segmentation map for the whole volume. The disadvantage with this 3D approach is that we might still lose important spatial context. For instance, if there's a tumor in one subvolume, there's likely to be a tumor in the subvolumes around it too. Since we're passing in subvolumes one at a time into the network will not be able to learn this possibly useful context. The silver lining with the 3D approach is that we're capturing some context in all of the width, height, and depth dimensions. This covers our 3D approach to segmentation.